Hello everyone, welcome to Scalar Spark. Today we begin an important core subject in electrical engineering, that is the power system analysis. This is Unit 1, and in this lecture we will going to cover the per unit representation, single line diagram, impedance diagram. Impedance, or sometimes we're going to call it as the reactance diagram, and we're going to study the network topology, bus incidence and network matrices, and formation of Y-bus matrix, okay. So these three constitutes the per unit representation, and these three constitutes the formation of Y-bus matrix, okay. So let us try to have a quick look at the Unit 1 syllabus. Try to have a quick look at this syllabus. In this Unit 1, we're going to study the per unit representation first, and after that we're going to study the circuit topology, okay. So in the per unit system, we're going to study the per unit quantities, single line diagram, impedance diagram. Sometimes we are going to refer it as the reactance diagram of the power system, and we will try to solve some numerical problems. So first we will try to understand what exactly is a per unit system, and after that we're going to cover the circuit topology. Let us try to understand the per unit system. The per unit representation, in the sense, actually by learning this per unit system, you're going to learn the foundation for entire power system analysis subject. If you understand this clearly, load flow, fault analysis and stability will becomes easier, okay. So watch this lecture completely and keep a notebook ready. Actually, giving a brief introduction to power system analysis. Actually, the power system consisting of generating stations, after that it can be connected to the transformers, and it is connected to the transmission lines, and after that we may have the receiving end side transformers, and after that we're going to have the distribution lines. In these distribution lines the loads are being connected, so it is the generating stations. Transformers, transmission lines, distribution lines, and loads. These are the major components of a power system network. So all these components operate at different voltage and power levels. Okay, so the generator is having the impedance value, and the impedance value is based on its own voltage and power ratings. Transformer is said to have impedance value and it is based on its own ratings. Transmission line is said to have some value of impedance and it is based on its own voltage level, and the loads are also offers some impedance or the admittance values, but it is based on their own ratings. Okay, so to analyze a large interconnected system manually, in actual values become complex. Actual values analysis of the actual values becomes the complex. So the engineers use simplified representations and the normalized values. Simplified representations and normalized values. Okay, that's why we're going to study the per unit system, single line diagram and impedance diagram. So now we will try to understand this per unit system. Okay, so actually the concept is that the every element is having its own impedance value, and if this impedance value is dependent upon its own ratings. Okay, so if the system is having one common base kVA and common base kV, we can calculate the impedance offered by the circuit elements so that we can provide the protection at appropriate locations. Okay, so if we want to provide the protection at appropriate locations, we have to convert the entire power system network with a common base kVA and common base kV. Actually, if you go through one or two numerical problems, you can get a clear idea about it. Okay, per unit representation. So try to understand these formulas. These are very important to solve a numerical problem. The per unit system is a method of expressing electrical quantities as a fraction of defined base values. Actually, the per unit value is defined as the actual value by base value. So here VA represents the actual value and VB represents the base value. Okay, similarly we can express the per unit current as actual current by base current. From this we can write down the expression for base current as base current can be written as total P equal to V into I. Okay, so similarly I equal to power by voltage. Okay, so we can write down base current as total power by total voltage. Next, coming to the per unit impedance, Z equal to ZA by ZB, that is actual value by base value. This base value can be written as base value, we can written as V by I, that is the base kV by base current. So we can substitute IB, the value of IB here. Okay, so that is KVB by KVAB. Denominator, in the denominator we are having KVB, that will comes into the numerator. Okay, now from this we can write down Z equal to Z actual by Z base. Z base in the sense we are going to place this right here, that is Z equal to Z actual into KVA base by KVB square. So from this expression we are going to write it as Z per unit volt equal to Z actual into KVA base volt by KVB volt square. So we are representing this expression in terms of old values and representing the same expression in terms of new values. What is the meaning of old value and new values? New values are nothing but the values that are selected as new base values, and old values are nothing but the original ratings. Okay, old values are nothing but the original ratings. Is represents the old values and new values represents the new base values. So remember, new values are selected by us. These new values are selected by us for the entire network, whereas the old values are the ratings that are given in the diagram. Z per unit new. So from these two expressions we can write down Z per unit new by Z per unit volt equal to KVA base new by KVB square into KVB old square by KVAB old. Okay, so we are making Z per unit volt move on to this side. Z per unit new equal to Z per unit volt into KVA base new by KVAB old into KVB old by KVB new square. So in the numerator and denominator we are having the square, so we can write down this as total square. Okay, so it is the very important expression for calculating the new base impedance. Okay, here we are having the theory part, you can go through it. These are the 5 expressions that you need to remember. So if you remember these 5 expressions, it will become very easier for you to solve the numerical problems very easily. Okay, the per unit quantities, it is nothing but in a large interconnected power system with various voltage levels and various capacity equipment, it is quite convenient to express all the electrical quantities like voltage, current, impedance in per unit values. The per unit value of a quantity is the ratio of actual value in any unit to the chosen base value of the same dimension. Okay, so per unit voltage. So earlier we have just simplified these expressions, and we are going to learn how these expressions have came. Okay, so per unit value equal to actual value by base value, it is a general expression, and per unit voltage equal to actual voltage by base voltage, that is VA by VB, and per unit current is actual current by base current, that is IA by IB. Next we will try to understand the per unit impedance. Z per unit equal to actual impedance ZA by base impedance ZB. So you can go through it. It is the general expressions where we have discussed here itself. Okay, so the change of base of per unit quantities, so it is the expression that is used for calculating the new per unit reactance. So now we will try to understand what exactly is a power system, per unit system, and what are the differences between absolute and the per unit quantities. So these are the general theory points that you can go through it. Advantages of per unit system. So advantages of per unit system in the sense, while performing the calculations referring to the quantities from one side to another side of the transformer, serious errors may occur, and these errors are avoided using the per unit system. Since the per unit impedance Z per unit refers to the primary and secondary side of the transformer is same. So if you are having a transformer in your problem, even if you start the problem from right side, or even if you start the problem from left side, we're going to get the same reactance diagram. The voltage, current and impedance expressed in per unit do not change when they are referred from one side of the transformer to another side. That's what here we are discussing. Per unit impedance of the electrical equipment is expressed within a range. Per unit values in terms of phase and line quantities should be the same. Manufacturers usually specify the impedances of the machines and transformers in per unit values, since they provide more meaningful information. Next, the per unit impedance referred to is either side of the three-phase transformer is same regardless of the three-phase connections. At last, advantage is the computational effort in power system is very much reduced with the use of per unit quantities. Okay, these are the general advantages that you can go through it, no problem. So we will try to solve the problems so that you can get a clear idea about the per unit system. So here you carefully go through the problems. Two generators rated at 10 MVA and 13.2 kV and 15 MVA and 13.2 kV. So here we are having the two generators respectively are connected in parallel to a bus. These two generators are connected in parallel to a bus. This bus feeds two motors rated at 8 MVA, 12 MVA, that is 8 MVA and 12 MVA. The rated voltage of the motor is 12.5 and the reactance of each generator is 15%. For generator it is 15% and the reactance of each motor is 20%. Okay, so it is the diagram. So in examinations sometimes the question paper may contain this diagram, and in some question paper you have to draw this diagram based on the information given. Okay, based on the information given you have to draw this diagram carefully. So draw the reactance diagram. So we have to draw the reactance diagram. So for here we are having the two generators. For this diagram it is the reactance diagram, that is the xg1, it is the reactance of generator g1, xg2 generator g2. These two generators are connected in parallel to the two motors, that is there is the motor 1 and motor 2, these two motors. So in this given diagram the generator is having 15% reactance with respect to these two ratings. Generator 2 is having 15% reactance with respect to these two ratings. Motor is having 20% reactance based on these two ratings, and this motor is also having a rating on 20% based on these power and voltage ratings. So the per unit concept refers to select the base values. Select a base values for the entire diagram So here what he has selected, he has selected these base values, these values as the base values. That is, the power rating is 50 MVA and the voltage is 13.8 kV. So how they are selected? You can select any arbitrary values. You may select first generator values, you may select second generator, you may select motor 1 or motor 2. Any reference values you may consider. So these are the new values. So these are the new values. So in the diagram we are having the old or the rated values. So in the diagram it is given that the old values are given and we are going to consider the new values, so that we will going to redraw this entire diagram based on these new values. Okay, for example, xg x new. So in the last formulas list we have observed the expression for Z per unit equal to Z per unit volt into kVA base old new by kVAB new into kVB old square by kVB new square. So we are going to apply or use this formula in order to calculate the generator motor equivalent per unit reactances. So x new, xg1 new, x old values. What are the old values? 15%, that is 0.15. MEAB new and KVB new. What are the new values? 50 MEA and 13.8. So he has selected 50 MEA and 13.8, and KVB old, MEAB is old. KVB old is 10 and 13.2. So from where we have taken this, they are the generator 1 old values. Okay, so these two ratings are the new values. Okay, so here we are having the new values taken from here, and whereas the old values that are being taken from here. Similarly for xg2 also we're going to calculate xg2 old reactance is 15%, and the new values are 50 MVA and 13.8 kV, 50 MVA and 13.8 kV, and old values are 115 MVA and 13.2 kV, that is 15 MVA and 13.2 kV equal to, we're going to get some values. Similarly for motors. Okay, and at last we are going to finally draw this reactance diagram, that is xg1, xg2, xm1, xm2. Okay, so it is the reactance diagram that is expected to draw. So after the completion of the problem, you draw this diagram so that you can get the full marks. So if you change the base values, what happens if you change the base values? In the sense, the formula is the same, only the thing is that, so earlier we have selected the 50 MVA and 13.8 kV. Now we are selecting 70 MVA and 16.2 kV as new base values. So for this also we can calculate, these are the new values. Okay, so here you can observe the comparison of these two diagrams values. So here we are having 0.697, 0.686, 0.464, 0.457, 1.04, 1.02, and last 0.694, 0.68. Almost the similar kind of values. The values follows the same pattern. Okay, so whatever we can select the base kVA and base kV as the new values. Okay. Let us now try to understand what exactly is a single line diagram. Single line diagram is the diagram where generators are connected, circuit breakers are connected, it is the bus, and again it is the circuit breaker, it is the transformer indicating the connections, it is the transmission line with circuit breakers, it is the second transformer, there are the loads and motor load, and it can be a generator load. Okay, so impedance diagrams, actually in case of impedance diagrams, if resistor is also asked, we have to write down particularly this reactance diagrams. So if resistance is not asked, we can simply consider the reactances. So these are the points which we have already studied. And there is an important derivation, that is the per unit representation of the single phase transformer. So a per unit representation in the sense, either if you move from left side or either you move from right side of a complicated power system network, you're going to get the same values. Here it is the proof. So in this proof, V1 by V2 is 1 by A, I1 by I2 equal to A. So based on the transformer turns ratios, you can observe on primary side we are having the primary per unit reactance. If you are having the knowledge on transformer turns ratio, you can easily understand these things. And on the secondary side also, Z per 2 per unit equal to ZS per unit and ZB per unit. That is the total is R per unit. Now try to understand the problems and the material. I have given the many number of problems, but we will try to so if you are having the transformer 5 kVA 400 by 200 volts 50 Hz single phase transformer has primary and secondary voltage leakage reactance each of 2.5 ohms. Determine the total reactance in per unit. So in this case, for case 1 we have selected the base voltage as primary base voltage. In case 2 we have selected a secondary as the base voltage. In the third concept, the primary side voltage is taken for primary per unit reactance. Secondary side voltage is taken for calculating the secondary side per unit reactance. So we're going to get the same values in all these three cases. So this problem clears the confusion that either we start moving from left side or either we start moving from right side, the per unit diagram will be the same. So they are the number of problems that are there. We will try to solve one problem so that remaining problems you can easily understand. The single line diagram of an unloaded power system is shown below. Reactance of transmission line is shown on the diagram. The generators and transformers are rated as follows: generator 1, generator 2, transformer 1, transformer 2. Draw the impedance diagram with all reactance marked in per unit. And one more important point is he has given to select a base of 50 MVA and 13.8 kV. So he has clearly mentioned that take the base MVA as 130 50 MVA and 13.8 kV. So it is the diagram. So from the given diagram, you first check that ratings, write down the ratings. They are the ratings that we are going to refer it as the old values. Okay, so all these ratings are the old values. What are the new values? 50 MVA and 13.8 kV. It is the new values. So from this we're going to try to solve this problem. So for the given generator, you try to mark up the zones or sections like this, separated by transformer windings, and section 2, and here we are going to have the section 3. So these are the old values and new values. These are the new values. In the diagram he has given the old values. So what happens when there is a device in section 1? The new values that are selected as 50 MVA and 13.8 kV. The second section, transformer will never changes the power. So the 50 MVA remains the same in all the 3 sections. Whereas the voltage changes from transformer. Voltage changes from the transformer. So previous section voltage, that is 13.8 multiplied by turns ratio, that is 220 by 13.8, that is V2 by V1. So how to calculate the base voltages in other sections? Previous section voltage multiplied by V2 by V1 equal to 220. So in the third section also, the previous section base voltage is multiplied by 18 by 220, that is V2 by V1. So where these are helpful, these are the new values and these are the old values. And the base impedances also we have calculated. Why? Because for a case of transmission line or loads, we need to calculate the base impedance. So it is the general formula for transformer T1, transformer T2, generator 1, generator 2, transmission line. How we are going to calculate? J180 is the data given on the okay. We'll try to understand the problem. Here there are a few more problems are being given here. So in the coming class we will make a review of this per unit system. Okay, so you can go through these number of problems we are having. These problems are also most repeated from the previous units. Okay, so try to go through these problems. All the problems are same. At the transformer we are going to divide the sections. At every section new power is constant, whereas the voltage changes from one section to another section. Okay, so you try to understand all these problems. Okay, in the next coming class we're going to start the incidence matrix. Okay, so it is about the per unit representation. So anyhow, in the next class we will try to make a review of per unit system or the per unit representation. Okay, if you found this lecture useful, like the video, share with your friends, subscribe to Scalar Spark, and comment your doubts below. Thank you for watching. See you in the next part, that is unit 1. Actually I have tried to complete in one session, but it is not at all possible. We're going to cover the Y bus matrix in the next session. Okay, thank you.